Hi, and welcome to part 2 of Unit 6. So this is all about two main types of energy, which actually fall under the same type. They both are types of mechanical energy. Mechanical energy is the sum of all your kinetic and potential. So that's what we're going to really focus on today. We're going to focus on looking at kinetic energy and potential energy. What is the difference between them? And what is the equation for them? Later on in class, we'll actually really work on the equations for them. All right, so let's talk about the first one. Kinetic energy. Kinetic energy is energy that is in motion. Anything that is in motion has kinetic energy. I'll repeat. Anything that is in motion has to have kinetic energy. So to find kinetic energy, since you're in motion, it's very easy. It's just kinetic energy equals 1/2 times mass times velocity squared. Now, someone may ask, well, since velocity has direction, does kinetic energy have direction? It actually does not. Kinetic energy is scalar. It's only magnitude. There is no direction. It's not a vector. To shorthand this, sometimes we write E sub k, which again stands for energy kinetic or kinetic energy, equals 1/2 mv squared. But again, we never say what the letters are. We say what they mean. So again, this says kinetic energy equals 1/2 times mass times velocity squared. The unit for energy, whether it's kinetic energy, whether it's potential energy, whether it's work, they're joules. Again, work and energy are synonymous. Okay, they are the same thing in theory. So they're both in joules. But there's a little chart here showing that anything in motion has kinetic energy. So what are the two main things kinetic energy depends on? Well, if we look at the equation, your kinetic energy depends on your mass, and it depends on your velocity. Also, side note, I don't know if you can tell, voice is a little out. I've been sick pretty much the entire winter break, so I apologize if I sound a little rough right now. All right. So the question is, what matters more for kinetic energy? Does changing your mass create a bigger change, or does changing your velocity create a bigger change? Well, let's look at a couple situations. Let's say this is our, I guess you could say, our control. This is our original. This is our baseline. Let's say we have a mass of 3 kilograms and a velocity of 2 meters per second. Let's find the kinetic energy for that. Well, kinetic energy, again, equals 1/2 times mass times velocity squared. So it'd be 1/2 times 3 kilograms, which is our mass, times 2 meters per second squared. Be very careful. When you put this in a calculator, you have to be smarter than your calculator. Sometimes if you put all this in your calculator, it'll give you the wrong answer. What it will do sometimes is it will multiply these two, multiply this, and then square that answer, which is wrong. Okay. Always remember the following. Please excuse my dear Aunt Sally. Parentheses, exponents. Please excuse my multiply, divide, my dear, add, subtract. I had to remember those for a second. I know I use parentheses here. These really aren't parentheses. I just use these to kind of separate the different variables so it's a little bit easier to see. But what you need to do is you need to square the velocity first and then multiply by these two things. So really it's 2 squared, which is 4. 2 times 2 is 4. 2 squared. So 4 times 3 is 12. 12 times a half, or half of 12, is 6 joules. So again, very easy equation. In class, we'll look at how to solve these if I want to find mass or if I want to find velocity. But for this video, we're just doing basic normal equation. So this is our standard, 6 joules. Now, let's change something. Let's double the mass. Originally, the mass was 3 kilograms. Now the mass is 6 kilograms. The velocity stays 2 meters per second. Same equation. Kinetic energy is 1/2 mass times velocity squared. So 1/2 times 6 kilograms, because I doubled the mass, times 2 meters per second squared. This time, if I plug all that in, I get 12 joules. So notice, when I double the mass, I double the kinetic energy. That is because kinetic energy and mass are directly proportional. I'll repeat, directly proportional. I used that term a lot back in semester 1. For those of you who are new, I don't know if you learned that in Mr. Wilson's class or if you came from a new school and you just entered our school this semester. Directly proportional means whatever you do to one variable, you automatically do the exact same thing to the other variable. Meaning, if I take half of mass, I take half the kinetic energy. If I quadruple the mass, I quadruple the kinetic energy. Whatever I do to one, I do the exact same thing to the other. This time, let's double the velocity. Oh, there you go. Whatever you do to mass, same thing happens to kinetic energy. Directly proportional. This time, let's double the velocity. Notice, the mass goes back to being what it was originally, 3 kilograms. But this time, I doubled the velocity. It was 2 meters per second. Now it's 4 meters per second. So I do kinetic energy, 1/2 times mass times velocity squared. 1/2 times, oh, I forgot to put 3 kilograms in there, I apologize, times 4 meters per second squared. So notice I have to square this 4 first. So 4 squared, 4 times 4 is 16. 16 times 3 is 48. Half of 48 is 24. Notice, when I doubled the velocity, I did not, I repeat, I did not double the kinetic energy. In fact, originally it was 6, now it's 24. How many times bigger is 24 than 6? It's 4 times bigger. So when you double the velocity, it quadrupled the kinetic energy. Why? It's all because of the square. Whatever you do to velocity, let's see if I can do that. Move that down a second. There you go. Whatever you do to velocity, the kinetic energy is squared that. So double squared, it's 2 times 2, that's 4. It would be 4 times bigger. What if I tripled the velocity? Well, what's triple squared? What's 3 squared? Good, it's 9 times bigger. If I take half the half the velocity, what happens to my kinetic energy? Well, half squared, for those of you who don't know, is 1/4. So my kinetic energy goes down 1/4, which is a big change. This is called directly proportional squared. It's proportionally squared. So whatever you do to velocity, you square that, and that's what happens to kinetic energy. So notice, a change in mass does the same change in kinetic energy. If you do a change in velocity, it creates a far greater change. So what matters more? A change in velocity matters greatly more because you are squaring that number. A small change in mass is a small change in kinetic energy. A small change in velocity can be a big change to kinetic energy. So again, it's all because of that squared. The other type of energy is potential energy. Big misconception. People think that potential energy is energy that is at rest. That is not true. You can be moving and have potential energy. And we'll look at that in a little bit. The definition for potential energy is just energy that's stored in an object. It's stored. And there's many different types of potential energy, but there's one main one we'll look at the end of this. 2 minor ones, though, are elastic potential energy. So it's the energy that's stored up in objects that stretch, like a rubber band. If you take a rubber band and stretch it, it stores up energy, and when you let go, it can fly across the room. The elastic that's in underwear, okay, that's also a type of elastic stored up energy. So anything that stretches, if you think about it. Chemical potential energy. So this is the energy that's in chemical bonds. So when you eat food, food has chemical bonds. When you eat that, it releases energy that gives your body the energy it needs to function. And then the main one, the absolute main one we're going to talk about is gravitational potential energy. I'm going to move my picture here. So gravitational potential energy is the energy that's stored in an object due to its position above the ground. Now, a lot of times we consider the ground to be the reference point, but it doesn't have to be. We'll look at numerous situations when we do the math with this where the ground is not the reference point. But gravitational potential energy is just how much energy you have relative to a reference point. So again, reference point goes back to motion. We talked about motion back in Unit 4. We're not going to do anything of frame of reference or anything like that, but just we're going to talk about a specific point, like relative to a diving board, relative to the roof, relative to halfway down from like a high dive to a low dive, something like that. It's just, it can be relative to any specific location. It does not have to be relative to the ground level. The equation for gravitational potential energy. So here's the other one that has another equation. It is mass times acceleration due to gravity here on Earth. Although if we're on the moon, then it's acceleration of gravity on the moon or wherever, times height. And this height is the height referenced or relative to whatever the reference point is. To shorthand this, we just say EG, again, gravitational energy is equal to mgh, but again, mass times gravity times height. What is the acceleration of gravity? This was talked about on Earth back in unit, well, we actually talked about it for forces. So what is the acceleration due to gravity here on Earth? Good, it's 9.8 meters per second squared. No matter where you are, everything falls on Earth at 9.8 meters per second squared. So what are the things gravitational potential energy depends on? Well, let's see. It depends on your mass, depends on the acceleration of gravity, and it depends on height. Now, for the sake of argument, we're just going to make everything here on Earth, so this is going to be a constant. It's always going to be 9.8 meters per second squared. So the things that can change are the mass and the height. So we can see that with these two pictures, if I just move my face. So notice we have two people dropping objects, one a small brick and a large brick, or maybe they're stones, who cares? So the question is, which would have a bigger potential energy, the small brick or the big brick? Hopefully you think the bigger your mass, the bigger your energy, you'd know, okay, the big mass will have the more potential energy. Here we have two identical bricks, but they fall from different heights. Which has more potential energy relative to the ground? Again, notice we can easily say that the higher you are off the ground, the more potential energy you have. And that's easy to think about if you think about people who do, like, think of trying to do a belly smacker off the low diving board versus off the high dive. If you do it off the high diving board, that's really, really, really going to hurt compared to doing it off the low dive, which will still hurt, but not nearly as bad as doing it off the high dive. And again, the reason why is you have more energy stored up the higher you are off the ground relative to the ground. So, but much like what matters more, mass or velocity, what matters more here, mass or height? Well, again, let's look at some situations. Originally, we'll say our mass is 1 kilogram and our height is 1 meter. So, gravitational potential energy is mass times gravity times height. 1 kilogram times 9.8 meters per second squared times 1 meter is 9.8 joules. Let's double the mass. I think I have a safe spot right here. There we go. I won't be in the way now. I doubled the mass. I kept the height the exact same. So again, potential energy, mass times gravity times height, 2 kilograms times 9.8 meters per second squared times 1 meter is 19.6 joules. So whenever you double the mass, I also double the potential energy. What's that called when if you change the one variable, the other does the exact same thing? Good. Mass and potential energy are directly proportional. They are directly proportional. Whatever you do the mass, the exact same thing happens to potential energy. Now let's look at height. Keep the mass the same as the original, but double the height. Again, potential energy, gravitational potential energy, is mass times gravity times height. 1 kilogram times 9.8 meters per second squared times 2 meters is 19.6 joules. Well, that's interesting. When you double the height, it doubles potential energy. It does the exact same thing. So again, this is also directly proportional. Whatever you do to height, the same thing happens to potential energy. So what matters more? Neither. They do the same thing. So here's a really good conundrum. What if you double the mass and double the height? That's not on here. What do you think happens to your potential energy? Again, if you double the mass and double the height. Good. Double times a double, it quadruples. Your gravitational potential energy will quadruple. It will go up 4 times. What if you double the mass and take half the height? Very good. There is no change because double is times 2, half is times 0.5, 2 times 0.5 is 1. So it won't make any change. It would be the exact same as if there was no change at all. Alright, last part. I know this video is going kind of long. There's a lot to talk about with this. It is very, very, very important to know, and I said this already, you can have potential energy and still be in motion. So you can have both at the exact same time. You can have both kinetic energy and potential energy at the exact same time, like on a swing set. Or here's a pendulum, which we actually have a video of Angel doing, and I'll show you that after this. When you're at the max height, when the object's not moving, because whenever something swings back and forth, it has to stop for a split second before it goes the other direction. And if you stop, that means your velocity is 0. Well, 0 squared is 0. So 0 times anything is 0. So your kinetic energy is 0. And since you're at the maximum height, you have 100% potential energy. And then what happens is, as you start to go down, your height decreases, which means your potential energy decreases. Well, what happens to that potential energy? It changes to kinetic energy. It means you're going to start to go faster. This is part of the law of conservation of energy, which we'll look at in the next video. And that's a really complex equation too. As it gets to the very bottom, when it gets to the very, very bottom, the height will be 0. So mass times gravity times height, the height 0, so mass times gravity times 0 is 0. So I have 0 potential energy. That means my kinetic energy is 100%. Whenever you are at the very bottom of a swing, a roller coaster, anything like that, that's when you always go the fastest. The fastest part of a roller coaster is always at the very, very, very bottom of the hill. The fastest part of a swing is at the very, very, very bottom of your swing. Then what happens is you start to gain height. As you gain height, you get potential energy because you're gaining height, and you're losing velocity. You start to slow down as you start to go up. That means your kinetic energy went down. And as you get up to the very top, again, you stop for a split second, so your kinetic energy goes to 0, and you have 100% potential energy. So it just shows you that potential energy and kinetic energy, you can have both at the exact same time. They just keep switching back and forth, back and forth. When you toss something up in the air, the maximum time you have the fastest an object goes is the moment you launch it. Here's the maximum kinetic energy. The moment you launch it from your hand, and then the moment you catch the object back in your hand. That's when you have the fastest or the most kinetic energy. You have the least kinetic energy and the most potential energy when the object you throw up in the air gets to the very, very, very top. Now again, when objects get to the very, very, very top, they stop moving vertically. They may move horizontally if you toss at an angle, but if you toss something straight up in the air, eventually it slows down and stops. When it stops midair, then it starts to fall back down. But when it gets to the very, very, very top of its when you throw it up, it'll have the maximum potential energy because it'll be at the highest point it can be, and it'll have the minimum kinetic energy, which means it stopped moving. So again, you can have both kinetic and potential energy at the same time. So to review all this, we talked about kinetic energy, energy in motion. The equation is 1/2 times mass times velocity squared. We talked about potential energy, energy that's stored. Its main type that we will really focus on is gravitational potential energy. That is mass times gravity, the acceleration due to gravity, times height. And then we also explored how you can have both gravitational and kinetic energy at the exact same time. So now let's look at a video of Angel kind of representing this and what happens when you let go of a very heavy object. So right now, Angel has a heavy mass up to his face. He's going to let go of that mass. He's not going to push it. He's simply just going to let go. Right now, that mass is at the highest point it can possibly be, which means it has 100% potential energy, gravitational potential energy. Since it's not moving, it has 0 kinetic energy. So what happens when Angel lets go of that mass? Sure enough, it starts to fall down. It will start swinging one way, the other direction. Right now, it's kind of blurry and hard to see, but it's probably at its lowest point, which means it's going the fastest it can go because it's at its lowest point, which means it changed all the way to kinetic energy, and now it has no potential energy. But it's going to start to swing back upward and gain potential energy and lose kinetic energy. Let's see if I can stop it in time. Ooh, pretty close. Let's just say that's the highest point. Now that object has gone up the other way, so it's gained potential energy, and now it's stopped, and therefore it has lost all its kinetic energy. So, because it has potential energy, it's going to swing back the other direction. The question is, will it hit Angel's face? Oh, that was pretty close. It does not. Now, in ideal circumstances, it actually would just barely touch his face. But the reason why it does not is because of friction, air resistance. If there was no air in that room, that heavy mass actually would swing right back up to Angel's face and stop the moment it touches his face. It wouldn't hurt him, it would just stop the moment it touches it, which is right where he let go. But because of air resistance, it actually it kind of, I wouldn't say absorbs some of the energy, but some of that energy, that potential energy, it changes to friction, which is thermal energy. So notice it'll never quite go back up to his face, but gets pretty darn close. So there you go. Again, this just shows you that you can have potential and kinetic energy at the exact same time. But in real life circumstances, all 100% of the potential energy will not turn into 100% kinetic energy. That's because of air resistance, of friction, which causes thermal energy. But that's, again, because of real life. In theory, though, it should 100% change from potential to kinetic, kinetic to potential.